I don't usually introduce myself or my work very much before going straight into my presentations. In this case, I feel that I probably should slightly. I need to give you a little bit of background of where some of this stuff comes from. So, first of all, I have a confession to make. I'm not a functional programmer. I'm an old school programmer. I do object orientation, and I like lambdas, and I do some of those sorts of things, but I'm not a functional programmer. So I'm not going to talk about algebra, I'm not going to talk about monads, I'm not going to be talking about those sorts of things. I think there's separate concerns when we're talking about this stuff, and I think often when we talk about reactive programming, the concerns get conflated. The reason that I think that I've got something to say on this topic, as well as helping to edit the Reactive Manifesto and making some contributions, is I worked on one of those projects that kind of comes along sort of once in your career. And this project was to build a low latency, high frequency trading exchange from blank sheet of paper. At the time when we started writing this, we didn't know how to do it. We hadn't got a clue. And so we did lots of things in order to try and learn what it was that we needed to do. And part of what we evolved through our experimental approach was, I think, what you'd describe as a microservice reactive architecture, but blisteringly high performance. And I want to describe some of the reasons why that is and some of the reasons how it works. And I'm going to sort of talk at a reasonably high level about some of this stuff. So there's not a lot. There is no code in this presentation. It's not detailed tech. It's kind of detailed, kind of at the computer sciencey level maybe, but there's no maths either that I can think of. So part of the reason why this stuff matters is because our world is changing. And people keep saying this to you at this conference, I think, but it's true. If you look at where we were just 10 years ago, a typical system was tens of servers maybe. It had seconds of response time and hours for offline maintenance, and probably dealt in gigabytes of data. That was a kind of normal, sort of reasonably large enterprise scale system in those days, I think. Now, large applications now have thousands of multi-core processors, milliseconds of response time or faster, 100% uptime, and petabytes of data. That's not unusual these days. If you just look at memory, I'm not quite old enough to have programmed ferrite core memory, but I used to have one of these, and my wife threw it away. I was really disappointed when she did. But this is a ferrite core memory unit. Each of these little magnetic rings is about 3 millimeters in diameter, and each of those represents a bit. So that block of things there is 8 bytes. Okay, this is an SD card, micro SD card. That's 8 gigabytes. So that's kind of where we've come. So this is a bit longer than 10 years ago. This is kind of 1970s technology. These sorts of things were in use around those sorts of time. But we've come a very long way. This is another one. This is just 10 years. So this one is 128 megabytes. This one is 128 gigabytes. The game is changing. And the tagline for the Reactive Manifesto is 21st century problems are not best solved with 20th century architectures. If we're building N-tier architectures backed by a relational database, that's not a really scalable option. It's not, as Jonas was saying in his presentation that kicked off this track, that's not how you build resilient systems. It's not how you build scalable systems. It's not how you build systems that you can deploy to all of the time. It's not how you build systems that can be elastic and that can grow and can shrink. So we came up. I was involved in the rewrite of the Agile Manifesto. Many of the ideas were in place before then, but we came up with a way of talking about it, and this is part of what we were talking about. So if we want our systems to be responsive, we want them to be able to react to our users efficiently and quickly. And in order to do that, they need to be resilient. They need to be robust in the face of failure and continue delivering services. If we want them to be resilient, we also need them to be elastic, to be able to stretch and move and grow and shrink to meet demand. And we need them to be message-driven to support all of those things. That's the underlying substrate that allows us to do these other things. And I want to describe a little bit about why I think that's the case. So first, reactive systems. So a reactive system is responsive. That means it responds in a timely manner. This is the cornerstone of reusability. This is really what people mean when they say it's unusable. You can have poor usability in terms of a mental model of the system underneath, but if it reacts well, it will get a better response than something that's got good usability and reacts badly. It's also quick to detect problems. We want to be able to understand when something's going wrong and be in a position to do something about that. We need them to be resilient. We want them to be responsive in the face of failure. We've got the obligatory Monty Python allusion here. We want them to be responsive in the face of failure. Resilience depends on replication, containment, and isolation, and delegation in order to make sure that we're able to contain failures and gracefully degrade the behavior of our system in order to meet demand and to be responsive. Elasticity is important, and it's kind of growingly important in the world of the cloud, where if you're using Amazon EC2 and you just kind of provision all your servers and you just leave them all running, you're going to get a very big bill at the end of the month. You want them to scale down as well as up. You want to have the right amount of compute to service the needs of your system. And to do that, we need to have a decentralized architecture with no contention points, and we need to be able to push behavior out and shard it in different ways. And asynchronous message passing is the foundation of this approach, of all of these properties. And that's what gives us the loose coupling, the isolation and location transparency that allows us to do these other things. If you go away from this presentation with one idea in your head, I want you to go away with the idea. I want you to go away with two ideas in your head, not one. The first one is that asynchronous messaging is the answer to many of our problems in computing, and the second one is it's not as scary as it sounds. So what are the properties of a reactive system? So they're flexible. We can compose them in different ways. They're loosely coupled. They're not tightly bound to one another, so parts of the system can evolve at different rates to other parts of the system. They're scalable. We can increase provision of service by adding new compute nodes, new versions of the service. They're easier to develop. And I think that you might doubt me on that one, but I'm hoping that by the end of the presentation you won't. I'm hoping I'm going to demonstrate some of the reasons why I believe that to be the truth. They're more tolerant of failure because they're asynchronous, and so we're not coupled in time, so something can go down and we can respond to it later when it comes back up, as long as we get the messages and all that kind of stuff. They respond to failure gracefully, and they're responsive to users. That's one of those four principles that we're aiming for. The weird thing about this is it's kind of fractal in architecture. These ideas operate at all scales. I was recently attending a course on lock-free low latency programming run by Martin Thompson, my friend that we were talking about earlier. And one of the things that he was describing was the way in which modern processors inside them are message-driven asynchronous computing units. Each of the cores are connected by a bus, and they pass messages between one another to get the memory into cache. So at the level of the silicon on which our code operates, the way in which our code is decomposed into parallel execution paths by the processor, that's a reactive system. It's a message-driven asynchronous system. But it also scales to the largest. This is the way that Netflix works and Facebook scales, and those sorts of things are built this way because this is what you need to do when you've got the sorts of levels of demand that we've been talking about, the levels of data processing and CPU count. The large systems are composed of these smaller reactive components. That doesn't mean that we've got to be doing very weird programming styles at every level of granularity, and I'll talk more about that later. It's one of the things where I think the conversation gets confused when we confuse the conversation about reactive systems and functional programming. There is some crossover because we're both talking about the use of, often talking about the use of asynchrony when you're talking about reactive functional architectures and reactive systems, but they're not necessarily the same thing. You can do one without the other. So I'm going to go through various pictures like this and just try and decompose this a bit. So first I want to talk about synchronous messaging. Now, if you look at the world, I think it's pretty much hard to refute that the world's pretty much asynchronous. And we programmers have kind of layered synchronous thinking on top of the world because it's easier for us to reason about. It's much easier for us to think about I want to add to my account balance, so I'm going to tell it how much I want to add, and then it's going to tell me that it's added it. That's easy to understand. It's simple, and my program stops and waits for that response to come back. But there are problems with that model. So let's imagine we've got these two components, and component A is invoked with some behavior, and it delegates part of that behavior to component B. So if we're talking in a synchronous model now, then there are a number of places where this conversation can go wrong. So there might be a bug in component A. There might be a problem establishing the connection to the communication channel to component B. We might get a loss in transmission as the message goes between component A and component B. There might have been a problem with component B connecting to the communication channel at its end. There might be a bug in component B. And we've got the same set of problems on the way back too. Now, in any distributed system, we have all of these problems. So if we're making a synchronous call, we have all of these problems. Now, there's a difficulty with this, with synchronicity, because from the perspective of component A, it can only know if there's a failure of its own or if it can't establish a connection. Everything else, it can't tell the difference. If it doesn't get a response, it doesn't know whether component B was broken, whether the message was lost, and so it's got all of these error cases to cope with. Worse than that, we're in the same situation, and component A is doing some processing, it delegates to component B, it's now got to wait for component B to finish before it can do any more processing. Only after component B is done can component A can continue processing. That's the kind of the definition of a synchronous call, right? The way that we get, so when we're building multi-user systems, the way that we get around that is that we start to think, oh, well, we can't have it block on just one thread, so we'll have to go multi-threaded, right? So now we've got lots of problems. So now we've added complexity to our implementation of component A. We've got to worry about all the problems of multi-threading, contention, avoiding shared state. Concurrent programming is one of the most difficult things that we do in our industry. And we have to do all of that just to get around the problem of, because one of these threads is waiting for an answer back from component B. Synchronous communication increases the coupling in both location and time between the components. It makes it more difficult for us to scale, and it makes us more exposed to more failure cases. Let's do the same experiment and think about what it looks like with the same thought experiment and think about what it looks like with asynchronous messaging. So now we've got the same situation. There's some behavior that's been asynchronously invoked on component A. And A is going to, I'm sorry, I'm getting ahead of myself. This is still a synchronous case. So this is a synchronous case where component B is now delegating to something else. In this case, it's talking to a database. And we've got additional failure modes, which are also hidden from component A. And we've just compounded the problem in terms of the failures that we've got to express back and get back to component A. So component A is even more at risk now. Worse than that, if there was a failure in the channel on the way back, what state's the data in? We don't know. It's indeterminate. And so we've got a code for all of those error cases if that's our world. So let's talk about asynchronous now. Say asynchronous case now. So component A is invoked. It delegates an asynchronous call to component B. It's done. It can carry on processing messages. It can process a new incoming call, or it can wait for a response. It's not got anything. It's not got anything else. So where can this break? Component B sometimes later sends a message back to component A. So where can this break? It can break in all of the same places, except the only two that matter are those two. And those are the two that component A can know about. It can know whether it's got a connection to the communications channel. It can know whether it's got a bug itself. The rest, as long as the messaging service, whatever the communication protocol, whatever you're using, will deliver the message eventually, it doesn't care because it sent the message. It's going to get there eventually. It doesn't matter when because it's asynchronous. It's not blocked. It's not waiting for anything else. So all of those other failure conditions, component A doesn't have to worry about. We don't have to code for those error cases. We don't have to worry about whether the database is in an invalid state or not. Our code gets simpler. It also means it can be single-threaded, so it gets even simpler. We can write these things efficiently that just process messages. They just flow through. The messages flow through our system. We take an input, we process it, we generate an output, and we move on to the next thing, whether that's a new input or a response from an output. They're all just messages coming in, and we all just process those messages on a single thread. This goes blisteringly fast. This is aligned with the way in which processes are architected these days. This means that your caches are likely to be more coherent. It means that you're not going to get contention. You're never going to get shared state. All of these things, if you do this efficiently. So let's talk a slightly more concrete example, because I know these abstract things can be hard to work out, and forgive me for being a bit cheesy, but I'm going to buy a copy of my book. So let's imagine that we've got a bookstore and somebody places an order for the book continuous delivery. Okay? In the synchronous case, and we're going to need to go to the inventory to reserve that copy of continuous delivery. It's this sort of stock control kind of idea. So in this case, in a synchronous case, at the point at which the order is placed, we've got to stop that thread, and we've just got to wait until the book's reserved. What if it's out of stock? What if the system's down? What if it's never heard of that book? All of those cases you've got to cope with if in the synchronous case somehow. Now let's imagine the asynchronous version of that same conversation. So we're going to order continuous delivery, and we're going to ask for the inventory to reserve us a copy. Sometime later, we'll get a message back saying that the copy's been ordered, and we can pass that message back up the chain, whether that to the user ultimately, to say that the book's been ordered. This kind of turns into, if you imagine the code in these things, what you end up with is kind of some relatively straightforward state machines that just manage the state through the flow of messages as the conversation goes on. What I like about this too is that the implementation of these things tend to start to look like that ideal kind of pure domain model. I'm a big fan of domain-driven design, and this is the closest that I've ever got to really implementing that software simulation of your problem domain inside each of these services, which is very nice to reason about, easy to test, all of those good properties. So let's imagine, let's just walk through this case once more. So now we're placing an order, and we've got a model of our book in our domain model, and it's in the state of reserving because we've sent the reserve message. Maybe that's down, maybe it's broken, maybe it's out of stock. We don't care. We're in a valid state, and there's nothing more to do right now. Maybe there's an order for another book. In this case, I'm ordering Better Aerobatics, which I was expecting you to be a bit more cryptic about giving Jonas's introduction. So that's also in the reserving state. The inventory doesn't even have to be working. It can be broken, or it could be just slow. We don't care. Sometime later, it could be nanoseconds, or it could be days. We're going to get a message back from the inventory, and we've changed the state of our book, saying that the book's now being ordered. This has a consistent view of the world. It's in a known good state. It's simple code, simple message exchanges are allowing us to do this. Of course, the trick, as people that talk about these sorts of architectures will always say, is getting the protocols right and getting the level of abstractions right. I want to dive just a little bit under the covers to just kind of reassure you. So this all sounds nice and easy. You've got these things in memory, just processing these messages and passing on. But what about when you turn the power off? What about if something does fail? How do you give the reliability? Now, the system that I worked on, because of the very low latency and high performance demands, we built our own reliable messaging system. And I'm just going to describe a little bit about it because I think it's useful to understand the properties behind the sort of architectures that I'm describing. I hope that you wouldn't have to implement this sort of stuff yourself in order to make this work, because you ought to be able to get this out of a box. But for now, I just want to describe what's going on. So here's our components again, and our component is fronted by a ring buffer, and it's got a ring buffer on the outside, on the outbound channel too. The ring buffer has a cursor and a series of slots. So when component A sends a message, it's going to populate one of the slots, and it's going to move the cursor on to the next slot, as so. At some point, when the thread becomes free or whatever, a separate thread that's independent from here. So this is, I said we avoided concurrent programming. We avoid it by pushing some of those concerns down into the infrastructure a little bit. At some point, we decide to forward that message on to component B. That's going to be placed into the input slot for component B. Now, when we designed this system, one of the reasons that we did it was because we wanted to be able to journal these things and cluster them. So we could, as part of the mechanism behind this, we would write these messages to disk, and we would write them to a cluster pair before they were forwarded to component B. So this meant that we had a durable system. We had a system that was capable of fault tolerance. Let's put some more messages into the queue. Now we've got a case where we've lost a message in transmission. We've sent message 4. This wasn't expecting message 4. It was expecting message 3. So it says, no, that's the wrong message. So I'm going to send back a knack saying I expected message 3. So this one resets its cursor, and then it can be populating more messages into the buffer, but next time it sends, it's going to resend 3, 4, and 5. This way we get idempotent messaging, we get reliable messaging, we get the ability to cluster and stuff. As an infrastructural concern, it's outside of the business logic of our component. That's not a concern that we have to worry about. So we get all of these nice properties. The system that we built was essentially a kind of application server. We could write a plain old Java object, we could write in-process tests against it, and we could expose it as a service using these mechanisms to allow us to communicate between the services and give us these properties that allowed us to build these asynchronous reactive systems. This sort of ability kind of allows us to decouple our components both in time and space. We don't care where they are. We can be broadcasting messages. The location doesn't really matter. And we don't care when they respond, because we're asynchronous. They will respond at a time that's convenient. Maybe they're down at the point at which we send the message, doesn't matter. Maybe they're there and they respond in microseconds, doesn't matter. We'll just respond, we'll just have a message like any other message come in when in response. This is one of the key properties that gives us the ability to make elastic systems, to be able to scale them up and scale them down. We can have observers of our system looking at what's going on and decide, this one's doing quite a lot of work, we need more versions of that in order to share out the work differently. Part of this isolation, it's important to be able for these components to share nothing. The only means of exchange of information between them is via the messaging channels. That's, again, what gives us this resilience and elasticity. So let's talk a little bit about isolation. So this is kind of a classic pattern. You have two components and you share a database. And now we don't have that isolation. Now we've got a point of a contention, potentially, point of failure. We've got to code things in a way to make sure that this is efficient. We can't upgrade these things independently. And so this isn't a good pattern. This isn't a good way of building distributed systems that have the properties that we're looking for. What we really want is that we want to separate these concerns. We want to be able to, if this thing needs a database and that thing needs a database, give them a database. But they're their own databases. They can be within the bounds of the component, the service. That's its business for how that works. If one of them needs an object database and the other one's a relational database, that's fine. That's not a problem. So we need to firm up these boundaries and make sure that the only means of exchange of information is via the messaging system. If we're going to retain the properties of location and temporal transparency that we're talking about. You can't isolate stress. Ultimately, if a system's under stress, it's going to show somewhere. It's going, as things go wrong, it's going to come out somewhere along the line. So the system as a whole needs to respond when it's under stress. It's unacceptable for a stress component to fail catastrophically and lose information that's important to the rest of the system. So we need those sorts of failures to be isolated. The example that I gave of the reliable messaging system is one means to provide some level of that of isolation so that you can kind of replay messages that happened earlier. The other point that's kind of it surprised me the first time I learnt this, but queues represent an unstable state. And I'm going to show that in a moment. So we need the idea of back pressure really to resolve this. So let's first look at the queues. So let's imagine we've got components A and component B again. And let's imagine that component A is slightly slower and component B is slightly faster. In this situation, the queue's always empty. Now let's imagine the reverse of that. So let's imagine that component A is slightly faster and component B is slightly slower. So apart from the start, the initialization of the thing, then the queue's always going to be full. So a balanced load in the queue is an unstable state. It's kind of on a knife edge. That can only occur when both of these are perfectly in step in terms of the rate at which they're processing things. And that's just not a stable condition. That's not a normal condition. This is a problem. What happens to component A now? Well, for most of us, what happens at this point is not good. What usually happens is that component A falls over. Maybe if we're doing well, our logging system lets our operations team know, and they all kind of set off alarm bells and start running around trying to figure out what to do next. That's not a resilient system. We need to react differently. What we need to do is that we've got to pass the problem back up the line. There's nothing else we can do. We can either fall over, or we can say, we can't do any more work at the moment. So we need to apply back pressure, and that back pressure needs to go all the way back up the line. Ultimately, that probably means to the user, you've got to find a way of slowing down the user. There are all sorts of different ways of applying back pressure. I came across a lovely one recently, which is start doing work on the thread that's coming in with the messages, and then you're consuming the resource of the thing that can send you messages to do the work, and you're starving out the supplier. But you can build in protocols that pass the back pressure up and start, giving an exception, or shouting a problem in some manner at the point at which you're trying to send communications because the system's under stress. One of the ideas that's often talked about in these sorts of distributed systems is the idea of eventual consistency. And it makes people nervous. And it's kind of understandable. And I think there's a key idea that's often missed when we talk about it. So let's imagine we have a user and they've got a view of the system. And they've got a view of components A and component B. Usually, component B is going to be producing a slightly different reflection of the world, and that's going to be reflected somewhere in the user interface. These could be on the same user interface, they're just kind of different aspects of the system. Okay? And the user makes a change in one place, and that's communicated to component B. Now, at this point, there's a difference in the perception of the state that different parts of the system in. Now, that makes a problem only if your separation of concerns allows it to make a problem. So let's imagine now that what we're talking about is, let's say it's the Amazon bookstore, okay? So this is your basket, your shopping basket, and this is your order history. Does it matter that they're slightly out of date in that context? I think it doesn't. It doesn't matter if we have to wait till some time later for that change to get picked up and reflected in another part of the system. As long as the boundaries of your design are kind of within appropriate bounded contexts that separate their concerns appropriately, then eventual consistency doesn't matter. It's a rare occasion when it does. And I think that's an important part of the design of software systems, is to identify the bounded context and make sure that the state's stable within the bounded context, and that bounded context makes sense in a business context. It's an important part of the design of these sorts of systems. We've talked a little bit about location transparency, but elastic systems need to be able to react to changes in demand, as we've described. And if we want to do that, location transparency is a really important idea, because that's the ability to be able to figure out that we haven't got enough compute horsepower, launch something else that's going to be able to deliver that compute horsepower, and start forwarding traffic for that new thing to service. If every component knows where every other component is by, location-specific addresses, you don't have that ability to scale up, because then you've got to distribute an address map all around everywhere. So you need these things to be able to send messages and not care where the receiver is. I think that the thinking is going further than that. We're getting to the stage where the infrastructure that people are talking about, and in some cases is there, it doesn't matter whether one service is on the same box as another or on a different continent. They can communicate with one another effectively. I mentioned already that distributed computing is becoming pervasive. And to be honest, as human beings, we're not very good at it. We're not very good at thinking about it that way. So we've got to find models that allow us to work in this way without having to worry about the very difficult concerns of concurrent computing and that kind of thing. I think unless you're a specialist, if you're working at that kind of level, it's going to be very, very difficult. And even specialists wouldn't be conflating the concerns of worrying about multi-threaded computing and concurrency alongside worrying about the domain problem that they're trying to solve. Those are concerns that need to be separate even by the best programmers if we're going to build efficient systems. And again, this is one of the reasons why ideas like asynchrony, message passing, and location transparency are important. So let's talk a little bit about that idea of scalability. So we've, again, got component A sending messages to component B. Okay, so that's one model. We've got a version of component B that processes all the messages, and that's fine. What happens when component B can't keep up with the demand? Well, we can build in the ability to figure out, based on the content of the messages, where to send them, and have two versions of component B that services different parts of the messaging. Maybe that's on certain ranges of accounts. Maybe it's on different types of messages. Don't know, but being able to break that apart is an option that's available to you when you've got this separation between the messaging of the system and location transparency. So I think that modern hardware should change our assumptions of the way in which we design and develop software. One of the biggest problems that we face is the cost of moving data about. RAM's not random access. Disk is not random access. SSDs aren't random access. Each of these things, in terms of performance, has a variable profile. Disks are the easiest to understand. Any time when you try and get a byte from a disk, you've got to wait for the disk to spin around to get the right sector. You may have to move the heads to a certain location to pick up the right track, and so on. RAM, because of all the caching, depending on whether you get a cache hit or a cache miss, there's a dramatic difference in the performance of that. Thousands of times different. SSDs are block devices. If you're writing data, that is a dramatically different time penalty to reading data. And all of these things, it's not straightforward. This stuff is more complicated than it seems. The other big change, certainly if you're as old as me, there's kind of the inbuilt assumption that I grew up with in my programming career was that RAM was fast, network was slow, and disk was somewhere in the middle. And that's just wrong. RAM's slow, network's slow, disk is slower. There are some networks that can be faster in some circumstances. We're getting to the point where there are certain network topologies that can be faster than a RAM access. Certainly disk is dramatically slower than networking. RAM's changing. RAM's changing. I think we've got massive non-volatile RAM is knocking on the door. It may be a few years down the track, but it's not very many years down the track, and that changes the game too. So we need to be thinking about new ways of architecting our systems. The old ways are built on the compromises that were imposed on us by certain performance profiles in the hardware that we were all used to. And those compromises, those assumptions no longer hold. This is the obligatory Conway's law slide. If you haven't heard about Conway's law, the idea is that the architecture of your system will mirror the organizational structure of the organization that created it. So if you have a hierarchical organization with siloed teams, you'll probably build a multi-tier architecture like that. If you have a group of small distributed cross-functional teams, you'll probably build something that looks more like that. This is kind of microservice territory. These are the sorts of systems that we're talking about. We're talking about these discrete units of processing, loosely coupled from one another using asynchronous messaging, which is microservices plus, to give us the elasticity, resilience, and scalability that we responsiveness that we demand. I've mentioned this idea a couple of times already, and it was mentioned by the previous speaker as well. Bounded contexts are kind of key to this in terms of being able to draw the lines around the components that we build appropriately. I was chatting with Jonas at lunchtime, and he was saying that it's often difficult to kind of figure out what the best programming model is to present for some of these things, because people take too simplistic a view sometimes and sorry, I'm putting words in his mouth that he didn't speak, but they will just make everything a remote communication call. You've got to think carefully about what the boundaries of a service are, what encapsulate these things, and those should be aligned with business context. You need to think carefully about the boundaries of the teams and what their responsibilities are, and they should be aligned with bounded context. Those might be several components within that bounded context to make it sensible distribution of work, but it's important to get these things right. What we're looking for all the way down the line is to minimize coupling. We're trying to minimize the coupling between teams, and we're trying to minimize the coupling between services, so that when we get to the point at which we have these asynchronous conversations, they make sense. They're simple and straightforward. They're not chatty. They're not, give me this bit or give me this byte, or, give me that number and I'm going to add them together. We need to design the protocols to make sure that they're sensible and loosely coupled. The kind of mental image that I have of this is, if you imagine an organization without any computers and a series of offices doing different parts of the job of that organization. Within those offices, it's down to the people to organise themselves however they like. And the offices communicate with one another by messages. Now imagine how you would design a system like that to work. That's kind of how we want to design our services. We want these simple exchanges of information. Ideally, if we were able to visualize the messages that flow between these components, it probably makes sense if they're kind of the sorts of things that somebody who understands the problem domain, a business user, would understand as part of the conversation. We want, place this order, this thing's been ordered, reserve this item. Those sorts of ideas, these sort of relatively high-level exchanges of information between the systems. And we should be looking to one of the key ideas of bounded context that's really important is that at the points at which we exchange information between bounded contexts, that's a point of translation. So even if both in two bounded contexts we have the concept of account, they're different. They're different versions of account. They might share a common key. They might be referring to the same count, but one domain's view of an account is going to be separate from the others. So here's a high-level, typical kind of architectural diagram of the system that we built. This is it's getting quite old, this system now. It's still one of the higher performing exchanges in the world. So we had our services, and our services were kind of reasonably large on the microservice scale for some of those things, but they were sensible bounded contexts. We had matching engines for where we would do deals, where we would do trades. We had account services, account management services where we would manage the live position of people that were trading. We had account history service where we would record what was going on further historically, what trades people had made, and so on. We kind of divided these up into three groups. So there's the idea of core services. Those were the services these were the seriously high performance things. These were the things that were doing our business logic. These were kind of the systems of record. The system of record was the in-memory state of these things, and these things could fly. They were servicing hundreds of thousands of messages per second very easily in microseconds. We had general services. These were kind of the slower, more traditional kind of services. Now, most organizations, I think these are the sorts of services that they would build in this kind of model. These things were often backed by a database. But as I said before, the separation of concerns that we had as a result of the way in which we'd organized our bounded context, the live data for trading was only existed in here. In order to trade, you didn't have to, you kind of went through the layers to get to here, but this is where trades happened, and you didn't have to go anywhere else in the process of performing a trade. You didn't have to ask anything else to do that. If you wanted to look up your account history, on the other hand, which was kind of what trades you did before, that's here. Now, eventual consistency means that would eventually be correct, but at the point, that the live point of trading, this wasn't precisely up to date with what was going on here, but it didn't matter because nobody cared if their account history wasn't microsecond in line with their live trading at present. They're separate concerns. We also had a bunch of what we call gateway services. These were translation services. So we were interacting with different protocols, different systems, different endpoints. We were providing public web access, public APIs. You could write your own bots to trade against this system. We were providing institutional APIs, so you would use the FIX protocol, which is a financial information exchange protocol that's common in the industry, and lots of other places. And sort of all external communications came in through one of these gateway services. These things were kind of border patrol, so they would translate messages into a form that the rest of the system would understand. The rest of the system would kind of talk using broadcast asynchronous messaging between all of the services. And then they would translate messages out to whatever protocol was relevant in order to make this work. This was not only a very high performance system, It was also the most efficient system that I've ever worked on in terms of being able to do new work. Because each of these services was single-threaded, even the seriously high-performance, high-tech things, because all of it was single-threaded, it was straightforward to reason about. Because it was a rich domain model, a simulation of our problem domain in memory, it was simple to reason about, and it was simple to test. We also had the really lovely property that if we saw a bug in production, we could take the messages that were from production, replay them through the system in a test environment and get it back into precisely the same state, and then debug it in a test environment. There are not many systems that I've worked on where you could do that to the same degree. This was a completely deterministic system in that case. It was also exceedingly scalable because we could just shard the messages at whatever level. If we needed more matching engines, we could add more matching engines. If we wanted more account services, we could do that. All of those things, wherever the contention point was. So where to start? Sadly, I don't think that there's infrastructure that precisely does what I've just described. I think that I know of 2 or 3 people that are working on stuff like that. Akka is one version of doing things. It does more than I've described, and in some ways less. There's a new thing from Cautio called Baratine, which was influenced by the LMAX architecture that I've been describing to you, and they've taken some of the ideas. That too does some things that I think are wrong, including supporting synchronous messaging, which I think is a mistake. I don't think we should be supporting synchronous messaging in these sorts of systems. So if you try these things, I think Akka is by far the most mature and robust. But take a look at these things if these ideas appeal to you and explore. But remember that the key constraints are around designing your services within those bounded contexts and making sure that the points of exchange are loose coupled at the protocol level, not just at the technical level. That's me. That's the end of my talk. So I think I do have a few minutes for questions. Thank you. Any questions?
How do we make the user asynchronous?
How can you make the user interface asynchronous? Is that the question? Yeah. Good. So it seems natural to be synchronous, but you've just asked me a question. You're still thinking. You're still doing other things, and now I'm coming back to you with an answer sometime later. So we can push the asynchrony out. We can design our interactions to do that. Now, the protocols on which commonly we work aren't necessarily built with those assumptions in. I think that's something that ought to change. I'm writing some software right now which has kind of got a web interface, and I've got push both ways. So I plug in something to my message channel, and when a service wants to notify the user of something, it can send a message, and that will asynchronously be delivered to the web page. That too is the way that the LMAX model worked. So then you can write a model in your web page, in whatever your favorite web development language is, or your user interface, whatever nature of user interface is, and respond to those events. Now, 99.99999% of the time, this will be as fast or faster than a synchronous call. But those few percent of the times when something's broken, it doesn't really matter. It's still going to be okay. It will catch up sometime later. You're going to avoid coding for awkward error conditions. It takes a mental switch. It takes a change in approach, I think, a little. But I do think it leads to simpler code. But it just takes a slightly different way of thinking about it. More questions?
Are there any benefits of using such systems in a local environment? Say you're making a video editor, something that's never going to be distributed across many systems or something like that.
I'll repeat the question. Are there any benefits in using this kind of approach in a local system where you're not aiming to distribute it? I think that there are. So I think that you gain the benefits of simpler coding practices because you avoid these error conditions. and you also get performance. This is a higher performance architecture. By measurement, I mean, you know, we measured the hell out of this stuff to get the levels of performance that we're talking about for the exchange, and we tried all sorts of different things before we got to this. And we tried all sorts of classic architectures. We tried doing clever things like allocating work to threads, and we spent more time allocating work to threads than we did actually running work on threads, which is why we ended up with the single-threaded thing. This is a very efficient way of computing. It's also the way that our processors work. It also aligns really nicely with the way that hardware is going. So I think it's an efficient use of hardware. So I think that I believe that there are benefits. If I'm honest, I don't want to write code any other way than this, because this gives me the freedom to write the rich domain models that I like to write as part of my development, and the freedom to be able to scale that if I want to and distribute it if I want to. So I think that there are benefits to this kind of architecture, even if you're writing mobile phone apps. I'd tend to start thinking about writing them this way. We've got to get to the level where there's better support from the tools and infrastructure around this. And as I say, I know a couple of projects that are working on building that support in various areas, and I hope it's coming soon, because I think it's an interesting step in programming approach. That's a great question. I'll just repeat the question. If we've got two teams looking at different bounded contexts and they're coupled in that they're exchanging information by messaging, who's responsible for the interchange between them? It's a great question, and I don't think anybody's got an answer. Everybody's talking about microservices at the moment. The organizations that are probably most mature at microservices at the moment are starting to feel the pain. And microservices give you some wonderful things. They give you the ability to scale out, have lots of people working on independent things, but the protocols over time get more and more important. And I think that Netflix, Amazon and people like that are starting to realize that, and they're starting to worry about how they can be more rigid in the definition of the protocols and the management of the dependencies. The other way, so for the classic kind of microservice architecture, many small teams, you get the great scalability, great independence of the teams, and at the cost of who's responsible for the cross-team communication. The other way of doing it is to build a monolith. You can still build a microservice architecture. You can still build a reactive system. The LMAC system was many individual services, but actually it was owned by the whole team, and it was released together as one. So we ducked that problem by, because the protocol was always versioned, it was always at the same level. We'd avoided the dependency problem between of multi-versions of the protocol by having it released by one team. And you can do that, and that works well too, but that comes at the cost of you go in the direction of a single monolithic deployment, a bigger test infrastructure. If you're doing continuous delivery and all of your tests, you need to scale that up better. You need to invest in that to get that working. And at some level, although you can still have quite a lot of autonomy in small teams, there's a little bit of compromise with that too. So I don't think that there's a silver bullet answer to that question. I think it's a genuinely hard problem, and I don't think anybody's got a perfect answer. It's a compromise either way, and you kind of takes your money, places your money and takes your choice.
What to do if you have to communicate with external system that is synchronous?
That's a good one. I tend to hide it in the gateway. So try and make the gateway hide the synchrony from the rest of the system. And that can be tricky, but it means that the gateway will be ugly and more complex than you want it to be. But that's life kind of thing. That's what you'd have to cope with in that circumstance. But I'd want to isolate it as far as I could at the bounds of the system. The kind of purist view is that you can't hide that synchronous synchronous style. So that's why you want, once you go down the asynchronous route, it's got to be all asynchronous all the way. But you can kind of compromise it. It's kind of the same problem with a database commit. That's kind of a synchronous action, and for me, that's usually too slow for me to want to take the cost. But you've got to if you want to commit the data to database. So there are ways of isolating it using the more that I think about it, asynchrony is kind of the fundamental communication protocol, so you can kind of build other things on top of it. So you can kind of hide that synchronousness with asynchrony by some clever tricks, but that gateway service will be more complex and more ugly than you want it to be. Sorry, repeating myself. Any more questions? No? Okay, I'll be around for the rest of the conference if anybody's interested.